Right. Now can you see my slides? All right, great. Okay, so this is part 3 of parameter estimations. So in the last class, we looked at parameter estimations for a single population mean, right? So what we have last time was we have a population, but we do not know the value of our parameters mean, mu, population mean, and therefore we're going to use the information from the sample in order to estimate the value of mean, population mean. So in this, for confidence interval, what we mean by this value is an interval. So what the definition of this interval is that if we manage to identify this interval, this means this interval has a probability of the population mean lying between two limits is going to be 1 minus alpha. Okay. So in the last class, we looked at confidence interval for a population mean, and this is the interval. So this is our lower limit, and this is the upper limit. Okay. Why is there a minus and plus sign? There's a minus and plus sign because the the value that we're going to base our estimate on is x bar, and x bar has a sampling distribution which is normal, and normal, as you know, is symmetric. Okay. So in this case, our marginal error, so the value of our limits depends on this point, best point estimate, x bar. Okay, so this is only true for mu because why? Because x bar is the best point estimate for mu. Okay, so therefore it's x bar plus minus some error. So this error can be calculated from the critical value of your Z distribution if it is from a Z distribution. Okay, this is only the basic formula for the confidence interval for population mean. But you know that there are many situations in which we do not know the information for all these value limits. So what we do is we will estimate the value uh, based on this is the algorithm that we normally base on, which is if we do not know the value of sigma, we're going to use an estimate of S, and then only we check the sample size if it's large or small. The sample size would determine whether you're going to use a Z distribution or a T distribution. Okay, but this is only true when you do not know sigma. If you do know sigma, if you do know the value of sigma, whether you know the population variance or population standard deviation, you will use the basic formula, which is a Z distribution, Z score ataupun Z value from a Z distribution. Why? Because by central limit theorem, if you know information about the population, therefore you don't need to estimate. And therefore, kan central limit theorem cakap kalau dia normal, it's going to be normal. So in this case, we do know some information for sigma from the population, and therefore we will use a Z distribution, regardless whether the sample size is big or small. Okay, so all that reflects the confidence is the way that you construct your confidence interval to estimate a single population mean. Okay, so I've written it better here. This is the algorithm that you need to remember lah. So therefore, you don't need to remember all these formulas. You just remember this basic formula, and then with that, you are going to use that distribution. The only thing that you might need to um, uh, note is this. You can just base your guide would be your formula sheet that will be given to you during exam, or your statistics table. Okay, for example, let's say you do not know sigma and your n is small, you need a t distribution, but a t distribution requires a degree of freedom. So this degree of freedom can be looked upon at your formula sheet. In this case, is n minus 1. You can see from these formula, these are all related to single population mean. X bar minus mu x bar. There's only x bar here. Okay, so reflecting this x bar. Okay, right. So that is all for last week lecture. So today we're going to look at another variant of in finding the confidence interval for the mean. This time it's when you have two population. Two population, in this case, we're not really interested to know the value of each one of them. This for these two population, what we're really interested in is the difference between the the mean of these two population. Okay, so pi for mu1 minus mu2 indicates that we want to estimate the difference between two population mean. Okay, so for example, let's say you have two machines that you want to compare with, or you have observations in which you have applied two different treatments. So all these, your observations would reflect the population observation for that particular subject of interest. For example, you've got machine A, so all these are maybe measurements of machine A. And if this population is machine B, you've got measurements of machine B. And you want to know whether there's any difference between the two means, the difference between the two means of your measurements of your from your observations. Okay, I hope that is understood what we're going to do today, which is to look at the confidence interval for the difference between two means. Right? Any questions so far? Response, please. Okay, right. Okay, so that is the premise of our discussion today. Itu je yang nak buat. Okay, now how do we construct this interval? So based on what we have learned in the previous class, again, when you want to estimate mu1 minus mu2, so we know what is the best point estimate for mu1 minus mu2. So best estimate is x bar 1 minus x bar 2. Yeah, mu1 best estimate is x bar 1, mu2 best estimate is x bar 2. So if you want to do the difference, that means so we can so your best point estimate is x bar 1 minus x bar 2. The reason for this, as I've discussed in the last lecture, is because why is the statistics is picked out to be the best point estimate, because they are unbiased and efficient estimator. Okay, right. So you already know from your chapter 2, the sampling distribution of x bar 1 minus x bar 2 is a normal distribution. Kan? This is the your what you have learned in chapter 2. X bar 2 is has a normal distribution with these parameters. Okay, so therefore we can treat the same way that we did for a single population mean, in which if we want to find the interval of these, we're just going to find the interval around this value of x bar 1 minus x bar 2, i.e. you can describe it as a, a any point estimate of x bar 1 minus x bar 2 plus minus some marginal error. Okay, so once we have these values, we can get the lower limit and upper limit. So you're talking about interval, so you have a lower limit and an upper limit. Okay. So similarly, when you have a normal distribution, to find the probability of that is through a transformation of this statistics. So x bar 1 minus x whatever ni bagikan ni. So from here, when you want to calculate your normal distribution, kan probability, whatever value that you have, you will transform that into this value based on this formula. So your marginal error will take form of this VAC value times your denominator, i.e. this would be your confidence interval. Okay, So this is the confidence interval for a two-sided confidence interval. Two-sided means that, for example, if you as I've shown in the last slide, so your interval is 1 minus alpha, let's say it's 99%. So this is the area of that 99%. So your upper tail and lower tail would form alpha over 2, alpha over 2. I'm sorry, this should be an alpha over 2 rather than a specific value. Let me just change that. Copy, this should be, so I'm just using, so this is going to be B minus the alpha over 2. Alamak, should, yeah, Z minus the alpha over 2. Okay, the point is the alpha over 2. Alpha over 2 is the area. Okay, so the corresponding point for this area, alpha over 2, you can get the value based on what is alpha is. Okay, this is also a point for the corresponding probability. Pro, this is the point corresponding to the area of probability here, which is minus the alpha over 2, because if vec and 0, 1, therefore the middle value is here is 0. That's why it's minus vec and plus vec. Okay, right. Going back here. So, so that's a two-sided confidence interval. Note that if it's one-sided, then it has to be alpha with one-sided. But most of the questions that we're going to ask you is going to be on the two-sided confidence interval. Right, so that's your basic formula. So notice that if you have this basic formula, that means you need to know this, you will get x bar 1 minus x bar 2, you will get from your sample observations. N1, N2 is your sample size, but sigma 1 squared and sigma 2 squared are information from your population. You can either get those values from your variance or your population standard deviation. So therefore, you would require these information to be plugged into this formula. As per single population mean, it will not all the time you would have information for these. So therefore, you need to estimate. Now, this one has a slightly, it looks complicated, but it's not really it's not complicated. You don't have to remember the formula. As I've said before, just remember the basic formula based on the situation. So, so there's an extension to the question. So in the last single population mean, you only identify whether you know the population variance. So in the previous case, for the single population mean, you only need to know whether you know sigma, because that's the only value that you need to know, and the sample size. Okay, but for two population variance, um, yeah, there are situation because there are two population here. So there's an additional condition that you need to check. Number one, beside the sample size, is this: if you do not know the population variance, then there is a possibility that the two variances are the same. Yeah. For example, let's say you want to investigate the marks for. Let's say you have here marks for, what do you call that, for students from faculty of engineering, and here you've got students from faculty of science. So you're viewing these as two populations. Okay. However, both of these faculties are from a university. So therefore, on some level, there might be the variation might be the same. Okay. So here, I mean, each one of them has got its own population variance, but since we do not know the value, but there is a possibility that they are the same. Now, if they are the same, Therefore, we need to estimate the combination of these two values, i.e., I'll write in your chat. So sigma P, so if you have equal or common population variance, you can estimate pooled pooled population variance or the pooled standard deviation. Okay, so here, so you need to calculate this. So how do you calculate that? Is through this formula. So if you can see this formula, this is the estimate of the pooled standard deviation, or we can write that as SP. Sometimes you can read sigma hat P or SP. So this is equals to a combination of these two information from two populations. So you've got S1 squared, obviously you get that from the first population, and this one is from the second population, divide by degrees of freedom of N1 plus N2 minus 2. Okay, so and thus this would be your estimate for the pooled standard deviation or standard variance. Kalau if you want a variance, you just square it up. Okay, and if you want a variance, then you don't have to square root it. Yeah. Now, once you've got this pooled uh, standard deviation or variance, therefore you plug it into this formula here, which gives you this formula here on the upper the equation on the upper hand here. Now, because of the same value here, therefore you can factorize it to SP. Okay, so SP times square root of 1 over N1 plus 1 over N2. So this would be your second formula. Okay, but if they are not the same, then therefore you just estimate just like you do, which is just to replace the value sigma 1 squared with S1 squared and S2 squared. Okay. So notice for this case, you've got n to be large. So n large, as you have understood it, as I've shown before, n large, therefore your distribution that you're going to use is a Z distribution. Unknown population variance and n large, so therefore is a Z distribution. Okay? All right? Is it clear? Okay. Right. So now, Z distribution. Okay, that's it. You don't have to memorize this formula because again, the formula will be given to you. Okay, so for example, here, this is the basic formula. So SP, if you want to look at SP, okay, let me just okay. So here, so this is the formula that we're looking at again. So in this formula table or formula sheet that you have on page 2 or in your final sheet that I've given on e-learning, you can see that the formula is already there. So you just need to identify whether it's common or not common. First, you identify whether you know the population variance or do not know the population variance. If you don't know, then you need to estimate. If it's common or it has an equal population variance, so you are looking at the formula that has SP. So the only formula that have SP is are this formula. This one is the one that have SP in the formula, right? So this is the one that have SP, sayang, in the formula, right? So there's a Z and a T. So how to know whether you're going to use a Z or T? So you just have to look at whether the N is large or small, which I'll be coming up to this slide. Okay, so here we have unknown population variance, and you either have a common population variance or not common population variance. That means they have different population variance. Okay, so again, if it's common, then you need to estimate using an SP. But since it's small, then you have a T distribution. And note that T distribution has got its own degrees of freedom. Okay, this degrees of freedom is n1 plus n2 minus 2. Okay, um, but if it's different and n is small, you still have to use a T distribution with a degrees of freedom as well. But this degrees of freedom can be shown is quite complicated, so I'm not bothered to write this here, but you can have a look in your benda ni. Oh sorry, yang ada at your ni. So this is the degrees of freedom for if you have different population variance. So note that you don't need an SPU here because you're estimating it through the respective sample variance. But since you have a T distribution, so it has a degree of freedom as shown here. Okay. If you have a common population variance and n is small, you still have to use a T distribution, but notice that the T distribution has a different degrees of freedom. Here you've got n1 plus n2 minus 2. Here you've got this lot here. Okay, right. Oh shoot. Okay. So to summarize, this would be your algorithm that you should be look for. So basic formula, let me just put it here. So this is your basic formula. Okay, your basic formula, you check whether your sigma is known or not. If it's known, then you use a Z distribution using this basic formula. Otherwise, if you do not know the value of your population variance, so this is really speaking sigma 1 and sigma 2 lah. So, but yeah, but you know that, but the two population means therefore you have got two population variance. So now if you do not know the value, therefore you need to go to another level of checking whether they have a common population variance or not. Okay, if they do have, then you use a pooled standard deviation or pooled variance. If it doesn't have it doesn't have any common or equal population variance, then you use the values of the estimate separately. But for both of these, you need to check whether your n is large or small. If it's large, then use the Z. If it's small, and use AT. I hope that's clear for you. So the only thing that you need to remember is this formula and that and that method of thinking in order to modify this formula. Okay. Let's look at an example. Now here you've got two kinds of thread being compared for strength. 50 pieces of each type of thread are tested under similar conditions. Brand A had an average tensile strength of 78.3 kilograms with a standard deviation of 5.6 kilogram, and brand B had an average tensile strength of 87.2 and a standard deviation of 6.3. Construct a 95% confidence interval for the difference of the population means. Okay, how can you tell? So you know that from this question, you know that you are trying to construct a 95%. What is the measurement that we're interested in for this confidence interval? what is the measurement? The measurement is the means, right? Okay. But here is not just the mean, but the difference of the population means. So yeah, so this is the difference of the population means. And from the information here, you would know that, let me just show you using the presentation slide. Okay. So this is 95% for CI mu1 minus mu2. Okay. And from the information here, you know that there would be two populations. Why? Because it says two kinds of thread are being compared. So you've got thread 1 and thread 2. 50 pieces of each type. So here you've got N50 and 50. Brand A had an average tensile strength of 78.3 and 6.5. So you might wonder, would this be from a population or a standard deviation, or from a sample? Now, obviously this is from your sample. Why? Because it's already given to you average tensile strength. So if this is from mu, why are we checking for this? So in this case, this is from a sample. This is from a sample, this is also from a sample. So therefore, these would be the information that you have attained. Okay? Now you construct a 95% confidence interval for the difference of the population mean. So basic formula is this. So in this case, do we know our population variance class? No, we do not know our population variance, yeah? No population variance. Therefore, we need to go down. Is it common? Is the population variance common between the two? Okay, no. So first we don't know the value of sigma. We do not know whether it's common or not. Okay. If we do not know, we will assume that they are different. Okay. So in this case, so looking down from the from the flow chart here. So and then so it's not known, sigma not known, and it doesn't have any common population variance. So therefore, we need to use S1 and S2. Um, is the sample size large or small? Is the sample size large or small? Large. Okay. Therefore, from this basic formula, you just need to change your sigma to S. Yeah. So that will still be maintained. So here you've got S1 squared, S2 squared, and then 95%. Therefore, this is 0.05 over 2, 0.025, and you need to solve for this. And you will get two values. Okay, for the lower limit and upper limit. Are we clear? Okay, it is quite easy, right? I mean, do not think about all these formulas. Just remember, just note down this basic formula. By the way, this is not. I don't think you can get this from any books. This is what I concocted. Basically, it is from the from the information of the theory, and then we just make a flowchart out of this. Okay, just to make it to simplify the procedure. Okay, let's look at another example. Tensile strength tests were performed on two different grades of aluminum spars used in manufacturing the wing of a commercial transport aircraft. From past experience with the spar manufacturing process and the testing procedure, the standard deviations of tensile strengths are assumed to be known. Okay, standard deviation of tensile strengths are assumed to be known. The data obtained are as follows. And if mu1 and mu2 denote the true mean tensile strength for the two grades of spars, find a 90% confidence interval on the difference in mean strength mu1 minus mu2. So here we're quite lucky because all these symbols are given to you. Okay, most of the time they will not be given to you. Um, so if you look at from this passage, it says the standard deviations are assumed to be known. So obviously, sigma 1 and sigma 2 will be given to you. Okay, right. So let's look at how to solve this. Okay, again, 90% confidence interval for mu1 minus mu2. So from this information, you can glean that this would be the information that you have. Okay, now, so in this case, since we know sigma, therefore, so since we know uh, sigma, therefore you can just use the basic formula and plug the values in and solve. Okay, yeah, I'm looking at the question somebody has posted. Um, is it always easy to pick info from the question? Um, well, you need practice. Moment, Ali, yeah, you need practice, all right, for that one. But it should be clear because otherwise, it's going to be a biased question if it's not clear to. It's just you need to get the right symbols out because if you got the wrong symbol, then we will assume a different information, right? Like for example, let's say they not they won't they will not give this to you in a symbol form. You just say, okay, sample mean is 7.6. Sorry, let's say this tensile strength is given 1 and 1.5. Okay, and the sample size information is given by 10, 87.6. So basically, if you assume this to be sigma to be S, then you would obviously be using a different formula, which result in the whole thing to be wrong. Okay, so it's important for you to extract the right information and the right symbol. Otherwise, you will use a different formula, and because in this case, let's say you're using an S, so you will definitely use a T distribution rather than a Z distribution. Okay, so information has to be correct, symbol has to be correct, formula has to be correct. By the way, for confidence interval, if you look at the steps, there are not that many. Yeah, so maximum I would say there's only 3 to 4 marks here. Four lah, I would say. So always we're not sure whether you're going to do a face-to-face final exam. I think test two is going it won't be a I'm not sure test one, but by the way, your test one is going to be a multiple questions exam. So it's going to be a summative exam. But for test two and for test two and final exam, you will be given a formative exam. So this means that it's going to be a written exam. So all your steps has to be really clear. So when you do a confidence interval type of question, I would um, like that you write down the formula first and then plug in the values. So just in case you got the formula right, at least you will get a point for marks there. Okay, and then plug in the values and solve. So yeah, so you'll get I would say 3, 4, 5 marks here, depending on the question. You will have more if it's from an SP because SP would have more calculation and method there. So more marks if you have that kind of question, which we will go to the next question. Next example. Okay, here. The diameter of steel rods manufactured on two different extrusion machines is being investigated. Two random samples of those sizes are selected. From the observed data, the sample means and sample variances for machine 1 and 2 are as follows. Okay. Assume sigma 1 squared equals to sigma 2 squared and that the data are drawn from a normal distribution. Construct a 95% confidence interval for the difference in mean rod diameter. Okay, again, 95% for the difference in mean rod. And from the information here, you would gauge of these information, right? So now the basic formula is here. And so you do not know the value of sigma. Therefore, you will use an estimate. But here it says, yes, let me just use my, okay. Oh, sure. Yep. Okay. So here you have, this is the information that you obtained, and using the basic formula. So sigma is not known here. So you go down. Is it common? Yes, it's common. Common because it says sigma 1 squared equals to sigma 2 squared. It's common, so you need to use an SP. Therefore, you need to use this formula here, SP, get the values, plug it in there, and because the sample size is small, the sample size would refer to the general sample size between the two. Note that uh, when you do an actual experiment, and if you have two population that you want to measure, I don't think it's wise for you to do one sample size to be larger than the other, because you want to compare the two, so it has to be comparative. So here you've got 15 and 18, so it is quite comparative. 15 sample size and 15 observations and 18 observations for your sample. It should be enough. It should be sufficient to make it comparable. So you don't want one to be 50 ataupun 100 and this one to be 15. So macam tak aci. Okay, ataupun it will be not be a balanced comparative sample size. So here basically we're going to assume that these two would have quite similar sample size. If it's large, both will be large. If it's small, both will be small. Okay. For electrical engineering, I once had a experiment with somebody from bio engineering. So normally, um, when you want to test a device on human beings, okay, so it's sometimes very difficult to get volunteers. Um, so in general, I would say for your type of experiment, you would have a very small sample size, not large, unless you do a massive experiment when you ask everyone from your whole faculty to do this experiment, like for example to measure a certain device for an electric bed, for uh for an electric bed. So you want to know the degree of for example the inclination of the bed. So it's very difficult to even for you to get everyone on board to test the bed, because the bed might have a certain limitation on the constraint of how many people they can put on the bed. So and well, so basically I would think for your kind of experiment, your sample size would be small, not large. Okay, unless in very special circumstances, maybe it's large, but I guess if would have a small sample size. Okay, so in this case, here you're using a T distribution. Okay, so a T distribution would have a degrees of freedom. In this case, your degrees of freedom would be N1 plus N2 minus 2. Therefore, it's 31. Okay, so that value can be obtained from kejap George. This value can be obtained from this t-distribution score. So you need, so this is 0.025, 0.025, so 0.02531, get the value, plug it in there, and then solve for that. Okay, coming back to your question. 0.35 and 0.9 is sample variances or standard deviation? Oh my god, I got it wrong. Sample variance, betul lah. Sorry. So sample, let me just change the question then. I'll just change the question. I just put sample deviation here. So it will be sample standard deviation. Thank you, thank you, thank you. Sample and standard deviations. Okay, it's easier. Okay. Okay. Sample standard deviations. Okay. Thank you, thank you. Thanks. All right. Okay. So so yes. So that would be that would be the solution for that. Okay. Okay. Do you have any questions so far? One more example and then we're done. Okay. One more example. Okay. This is now we're looking at the nature of your experiment. So in the previous examples, we clearly have two population, and then we take measurements from those populations. For example, here you've got steel rods measured on two different extrusion machines. Okay, so you've got, basically this is machine A, machine B. Okay, but in this example, we have observations in which we apply two methods. Oh, sorry. Okay, back semula. Tang, madam, why we use SP since S1 and S2 is different? Because Tang, we're using SP because this is for exercise 3, is it? So for exercise 3, we use XP since the uh, the question, the passage, the problem assumes that the population variances for the two relation are equal. A, they have a common relation, variances. So here in exercise 3, the samples might be different. Okay, but on a higher level, the population variance are assumed to be equal. I mean, let's say I have a population variance that I know to be equal, but if I take sample size, the values uh, would clearly not reflect the population variance. This is observations from only this 15. From this 15, the variation within that is only 0.35. And the variation between the observations in here only from the 18 is 0.9. But here it says the population variance are equal. Okay, so if you use all the information from the observations from the population, then you know that population variance are equal. So those are the key things why we're using an NSP. Okay, Tang? So you need to be looking out for apa tu statements that says that it is equal or common. Okay, so you need to look out for those kind of statements to indicate whether you're going to use SP or not, an estimate of the pooled variance or pooled standard deviation. Okay, right. Okay. Now, this example um, reflects a different type of experiment. If you look here, it says an article compares several methods for predicting the shear strength for steel plate girders. Data for these two methods procedures applied to 9 specific girders are shown at the table below. So here you all have 9 observations, but each observation is applied to 2 different methods. So for method 1, for example, girder 1, when applied to this method, Carl's rule method, you will get an observation of 1.186. So this is an observation of 1.86. But if you use the same observation to the same subject, so this subject is applied to method 1, you get 1.86. When applied to method 2, it has 1.061. Okay, and it also gives you a difference value. Okay, so just for example that you have, for example, you have student A applied to 1 month. It uses what do you call that, diet uh, apa tu, like apa nama that, Atkins diet say, and they measure the punya weight. And then another one, it uses another method with, for example, high fiber diet. You got 1.061 as the weight. Okay, so that means here you are going to assume each subject are going to be applied to 2 different methods. Okay, so obviously in this method you can calculate the difference because they are, so this is the difference of observation from subject 1. So here it has 9 subjects altogether, all applied to the different methods. Okay, so how are we going to view this problem here? Now there are 2 ways for you to do this. Either you apa tu, so this form of question is what we call a paired experiment or paired observations, because the samples are not independent. So these samples are not independent. The subjects are clearly independent, but the observations here, the sample observations, are not independent. They are dependent. Okay, so you can do this. You can view this observations by 2 methods. One is view it as 2 different population. That means method K and uh, method 1 and method 2. So they have 2 different population. It is not wrong to do this, but it's called an unpaired, which we have been using before. Okay, all the examples that we have done before, done previously, is based on 2 different population. Okay, and therefore you would use in this case, and you do not know your population variance, but you can calculate each one of your sample size and your standard deviation or variance from the sample using the information here, right? And you will be using this formula because it is not common and it's small, so you use this formula T with the complicated degrees of freedom. Okay, so here you're going to use this formula here with the complicated degrees of freedom. Okay. Now, but if you view it, you can also view this observation from a single population. But if you use a single population, the observation here are not the methods, but the difference between the methods. So your observation is going to be 0.125, 0.159, 0.259. So these will be your observations. Okay. So in this case, you're going to view the sample as a paired sample, and therefore you're going to use a single population mean to estimate. So in this case, you're going to use what? You're going to use you don't know mu. You don't know. Let me just delete this. Confusing. Okay. For here, you're going to use you do not know sigma, and therefore n is small, so you're going to use a t distribution with s1 s s d squared over n, which is 9. Okay, let me find this apa tu, mana dia punya. I'll find the formula for this would be on 3rd April 2nd. I don't have the formula here, but you know what to use, eh? So yeah, let me just check lah terus. Sekejap. Cuba eh. 2 min F min. Let me find the formula for you. In this case, going to use. Yep. You're going to use this formula here. Copy that. So in this case, you're going to use this formula. Okay, where this is going to be your SD. This is going to be your SD. Oh, shit. D, and this is going to be your XD. Okay, right. So this is the formula that you will be using. But here it's not x1 or x2, but it's the difference of, because your observations is as so. Okay, right? Okay. Um, and you solve just like what you normally do lah. So just to note that you might not get exactly the same answer. Why? Because if you look here, your marginal error, I mean, you x bar 1 minus x bar 2, you might get the same answer lah, because it's the difference. Okay, the difference of this should be the same as difference of that. But if you look at the marginal error, you're going to use a different value altogether. In particular, is on the degrees of freedom. If you look at the degrees of freedom, here you're going to have n minus 1 to be 9. 9, right? N minus 1 to be 9 plus 8, sorry. 8. Whereas here, you might get lah, because you need to use the complicated degrees of freedom to get the degrees of freedom, which involves you using the value of your what you call that, of your S and your N and whatnot. So it might have some difference in the degrees of freedom. Okay, and therefore your interval might be slightly different. Okay. So both of them can be used, but it's more efficient for you to use a paired confidence interval. But for exam, both of them can be used as well, because we're not going to stress on the paired or the unpaired observations. Okay? Do you have any questions so far? Okay. No, no question. Eh? No question. Any question? Um, since you all have the pirated version of Montgomery. I'm not gonna. I mean, like I've no comment on that, because obviously it's a pirated version of Montgomery. So you've got so many exercises to do and try on. Okay. Um. So yeah, you can start with the ni. So your test two would involve all the I guess your test two would involve apa ni? Chapter 3 and maybe chapter 4 or maybe chapter 3 only. I am not sure. Okay. All right. Any questions? Response, please.